Calculus fans, welcome a video on arc length and curvature for vector calculus. We'll be going back to arc length in discussing it as it relates to these curves in 3 space. We'll talk about a new concept called curvature, and then we'll wrap it up talking about the normal and binormal vectors to a space curve. So let's start off with arc length. Remind you that we've talked about arc length before. If you have a curve parameterized in R2, x is f of t and y is g of t, then the arc length L is given by an integral where the integrand is the square root of the sum of f prime and g prime squared. Okay, this is something we did before, and this is a familiar definition for arc length. It turns out that this definition exactly extends in the case where we have a space curve in R3. If we have a space curve in R3 defined by f, g, and h, similarly, the arc length of that curve where the parameterization goes from a to b is exactly the square root of the sum of those derivatives squared integrated from a to b. Now, I'll point out that in both these cases, that those arcs sort of look like the integral of the length of a vector. In both cases, in the parameterization in R2 and in R3, the integrand turns out to be the magnitude or length of that vector that gives you the space curve. So that's how we express our arc length generally now that we know about vector valued functions. In general, if you have a space curve defined by vector r of t over an interval from a to b, then the arc length is the integral of the magnitude of the derivative of that vector valued function with respect to time. Okay, this is something we can usually compute, and it can be messy at times, but it gives us a nice, concise way to describe the arc length. Here's an example. Let's go ahead and find the length of that helix from P to Q. Okay, so in order to do this, we need an expression for R prime, and then we need to integrate that expression, the magnitude of that expression over the interval from a to b, which in this case turns out to be from 0 to 2 pi. So here we see that when the vector valued function r is cosine comma sine comma t, that the vector valued function r prime is negative sine comma cosine comma 1, and we can find the magnitude of that vector valued function, which turns out to be just the square root of 2. So we'll go ahead and integrate square root of 2. So point out that the point P at 1, 0, 0 corresponds to t equals 0. The point Q at 1, 0, 2 pi corresponds to t equals 2 pi. And the integral from 0 to 2 pi of the square root of 2 turns out to just be 2 pi square root of 2. Okay, super. I'll also point out that, as we've seen before, the same curve might have a different parameterization. So here is a different parameterization of the same curve. In this case, the parameterization is cosine 2u, sine 2u, and 2u, where u instead goes from 0 to pi. Now, of course, if we travel that same curve, just using a different parameterization, we should still get the arc length and the same arc length, and we do. And this concept is known as saying that arc length is independent of parameterization. Okay, now just like we did before when we discussed arc length, one thing we can do is discuss the arc length function. So the arc length function is a way of writing down a function of t that describes arc length starting at a and going out to some unknown value t. Okay, so again, this is a function of t, and this arc length function allows us to think of the arc length as a function of time. I'll point out here that this integral is in the form of the fundamental theorem of calculus. We can take a derivative of the left-hand side with respect to t. And when we do that, we see that the change of the arc length function with respect to t is exactly the magnitude of the velocity or the speed. So this is something that we can sort of make sense of, and it turns out to be a convenient way to parameterize the curve with respect to arc length and instead of with respect to the parameterization t. So here's an example. Let's go ahead and find the arc length function for this curve we looked at before, starting at 1, 0, 0 and increasing in t. So we saw previously that this curve has the magnitude of r prime equal to the square root of 2. We can express the arc length function s of t as the integral from 0 to t of square root 2 dt. And this again allows us to parameterize the curve with respect to arc length s instead of with respect to the parameter t. So here's that reparameterization of the curve in terms of the arc length, and now 1 unit of s corresponds to 1 unit of arc length. So we know exactly where we are if we've traveled 1 unit down the curve. We just have to plug in s equals 1. That's a pretty convenient, again, way to describe a parameterization. Okay, move on with the discussion of a new concept called curvature. So we say that a space curve C is smooth on some interval I if its derivative r prime is continuous and r prime isn't 0. Essentially what this does is just ensure that there are no cusps, no corners, that everything makes a nice continuous turn. Okay, so these are the kind of curves we're dealing with, so-called smooth space curves. Also a reminder that the unit tangent is given by the derivative r vector prime of t divided by its magnitude. So this is a unit vector that tells us the direction which the curve is changing. So our intuition about curvature is to try to measure how fast that unit changes in time. And we'll go ahead and parameterize with respect to arc length here. So kappa is the variable or the Greek letter describing curvature, and again, it's how fast the unit tangent changes with respect to the arc length. So you can sort of think about being a Calc 3 superhero walking along a curve. If you walk far and your unit tangent doesn't change much, your curvature is small, and if you walk a short amount of arc length and your unit tangent changes a lot, then your curvature is big. So here I've tried to draw two space curves and tried to sort of make the distance between those dots approximately the same, to try to imagine having sort of a fixed amount of arc length. You can imagine that the unit tangent doesn't change so much in the first one, but does change a lot in the second one. The second one has a larger curvature. The first one has a smaller curvature. Okay, this parameterization d vector t ds ends up being a little bit clunky, so an alternate form of the curvature is the vector t prime in magnitude divided by the vector r prime. So to see this, just recall that we just saw that the derivative of the arc length with respect to the parameterization t ds dt is given by the magnitude of the vector r prime. And we can use the chain rule here. This is just the chain rule to show that d capital T dt is d capital T ds times ds dt. This gives us an expression for d capital T ds that we can substitute in and find an expression for the curvature kappa of t. Okay, this ends up being a convenient way to express curvature. Here's an example. Let's go ahead and find the curvature of a circle with radius a. So we'll do this by first inventing a parameterization for the circle. Okay, so here's everything involved in that calculation. Once we know that the circle has parameterization a cosine t I hat plus a sine t j hat, we can find the derivative. We can find the magnitude of that derivative given by a. We can find the unit tangent, which is just given by this vector. We can find the derivative of that unit tangent, given by this vector. And then we can find the curvature, which is just given by the derivative of the unit tangent in magnitude divided by the derivative of the parameterization r in magnitude. So it ends up just being 1 over a. The intuition here is that the bigger the circle is, the smaller its curvature is. Okay, it turns out that sometimes this form can be kind of clunky too. T vector prime in magnitude divided by r vector prime in magnitude for the curvature. So there's a second alternative form for the curvature, and it's given here. An alternative form for the curvature is given by the magnitude of a cross product divided by the magnitude of the derivative of the vector. Now this looks a little bit difficult too, and I won't lie, it takes some work. So that work it takes is a downside. It's still computationally expensive. The upside, of course, is that it only involves r prime and r double prime, so there's no computing quotients and taking their derivatives. I'll state this result without proof. If you want to go through the derivation of this expression for the curvature, I'll point you to the textbook. It's right in there. Kind of a neat derivation that depends on the fact that unit vector, that capital T is a unit vector. Okay, one last thing to do with curvature, we can identify the curvature of a planar curve y equals f of x. And we'll go ahead and do this using that cross product formula we just derived, as well as a parameterization for this curve. So here's a super common parameterization you can always use for a curve y equals f of x, is to parameterize the x coordinate by t and parameterize the y coordinate by f of t. So what's left then is to compute r prime, r double prime, look at their cross product, and go ahead and compute that quotient that we had on the previous slide. So here's that cross product. R prime cross R double prime is I plus F prime J cross with F double prime J. Of course, distributing, this is F double prime I cross J and F prime times F double prime J cross J. Now, of course, J cross J is just the zero vector. The cross product of the vector itself is 0. And I cross J just gives you back K. So this cross product reduces simply as F double prime K hat. So a quick computation gives us that R prime in magnitude is this square root. R prime cross R prime in magnitude is just the F double prime. And when you plug that into the expression on the previous page for the curvature, this gives us the expression you see here, F double prime divided by 1 plus F prime squared, all to the 3/2 power. Okay, so this is a super cool expression for curvature. It tells us that curvature is related to the second derivative, which you might expect, but it also has to do with the first derivative as well. Okay, so you can make curvature smaller by making the first derivative large and keeping the second derivative the same. Okay, end our discussion today with a discussion of the normal and binormal vectors. So again, a quick reminder that the unit tangent capital T of t is given by vector r prime divided by the magnitude of vector r prime. So again, here the interpretation is that if we're thinking about a space curve C and we're traveling along that curve, that the unit tangent is a unit vector that tells us the direction we're traveling at a moment of time. Now, here's the first observation. The first observation is that there are a whole lot of vectors that are orthogonal to that unit tangent. The second observation is that since the magnitude of this tangent vector is always 1, it's a unit vector, we know that the tangent vector dotted with its derivative, t prime, is 0. So this gives us a specific way to talk about a specific vector that's orthogonal to this vector. That is, vector t prime, or any scalar multiple of that vector, is a nice vector that's orthogonal to t. So here's the definition of the normal vector. The normal vector, n of t, is given by a unit vector that's parallel to t prime. So we define this to be the normal vector. Okay, so now any space curve always has a tangent vector, a unit tangent, and a unit normal, and those are orthogonal. And of course, if you want a third orthogonal vector, all you have to do is look at the cross product of those, and we'll call that the binormal. So the unit binormal t cross n is a third vector that's orthogonal to both of those. So since t and n are orthogonal and b is orthogonal, the three of those are mutually orthogonal. Okay, so here's a quick summary. Given any space curve defined by r of t, the vectors capital T, capital N, and capital B, those form an orthogonal coordinate system of unit vectors, or sometimes you call this an orthonormal system. Okay, let's go ahead and have a look at an example. Here is a space curve defined by sine of 2t minus cosine of 2t in the j direction plus 4t in the k direction, and we'll go ahead and compute t, n, and b for this curve. And it's not a particularly difficult computation. It just takes cranking out some derivatives and looking at magnitudes. So here's a computation for the unit tangent. It involves the derivative r vector prime and the magnitude of that derivative, which I've omitted the details for, but you can find quickly to be 2 square root of 5. So again, computing t vector requires taking r prime divided by the magnitude of r prime, and here's what you get. Now similarly, to get n, we just take the magnitude of t prime divided by its magnitude. So here's that computation. Capital T prime is negative 2 over root 5 cosine 2t in I hat plus 2 over root 5 sine 2t j hat. And again, omitting the computation here, the magnitude of that vector is just 2 over the square root of 5, giving us the normal vector. Now, again, the binormal vector is just the cross product of those two, and that turns out to be a pretty quick computation. Also, I'll omit those details and just write down that binormal vector. So again, the computation doesn't quite all fit here, but it turns out to be negative 2 over root 5 cosine of 2t I hat plus 2 over root 5 sine 2t j hat plus 1 over root 5 k hat. Okay, one more concept here. We can think about planes formulated by those vectors. The plane formulated by hang on, I'm going to back up just a second and come back to this. Sorry, I didn't quite finish this previous example. So the point P corresponds to the parameterization value of pi over 2. And if we plug in that parameterization value to our vectors t, n, and b, we end up with these 3 vectors. And it's quick to see that they're all unit vectors, and it's also quick to see that they're orthogonal. Okay, so go ahead and talk about the planes. I'll point out that the plane formed by n and b is called a normal plane. The plane formed by t and n is called the osculating plane. And these planes actually, by the formulation of t, n, and b as an orthogonal system, have a natural unit vector. So you'll recall that we can always form a plane by any 2 vectors. Of course, the normal vector to any plane is a vector that's orthogonal to those 2 vectors. In the case of the normal plane, the unit vector t plays the role of the normal vector, and in the osculating plane, the unit vector b plays the role of the normal vector. So we'll go ahead and write down equations for the normal and osculating plane to this last parameterization we discussed. We saw that the unit tangent at pi over 2 was minus 1 over root 5, 0, and 2 over root 5. And of course, the binormal at pi over 2 was 2 over root 5 0, and 1 over root 5. So we'll go ahead and use r naught to be the vector pointing to this point P, 0, 1, 2 pi. And then in the case of the normal plane, n dot r equals n dot r naught, we'll use the tangent actually as the vector that's normal to that plane, gives us negative x plus 2z equals 4 pi. And the osculating plane, we'll use the binormal as the normal vector to that plane, 2x plus 4z equals 4 pi. Okay, a lot of information here. Hope you've enjoyed this video on arc length, curvature, and then normal and binormal vectors. Have a great day, and we'll see you next time.